Leo's Tech Talk. Video 7. Radio wave propagation characteristics. Radio waves rarely travel in a perfectly straight path from a transmitter to a receiver. As they propagate through the environment, they interact with various objects, surfaces, and atmospheric conditions that can alter their behavior. These interactions influence signal strength, coverage, reliability, and overall wireless performance. Understanding how radio waves propagate is essential for designing, deploying, and troubleshooting wireless networks. Key propagation characteristics such as reflection, refraction, diffraction, scattering, absorption, polarization, and fading determine how signals travel through real-world environments. Radio wave reflection. One of the most common propagation characteristics of radio waves is reflection. Reflection occurs when a radio wave encounters a large, smooth surface and bounces back instead of continuing along its original path. During this process, some of the signal's energy is lost. Similar to light reflecting from a mirror, the angle at which the radio wave strikes the surface, known as the angle of incidence, is equal to the angle at which it reflects away. When radio waves reflect off walls, ceilings, floors, buildings, or other surfaces, multiple copies of the same signal can travel along different paths and arrive at the receiver at different times. This phenomenon is known as multipath propagation. In a multipath environment, the receiver may receive several versions of the same signal, each having traveled a different route. Some signals may arrive earlier, while others arrive later due to the longer paths they have taken. These reflected signals can interfere with one another, causing signal distortion, reduced throughput, increased packet retransmissions, and degraded Wi-Fi performance. Fortunately, modern Wi-Fi technologies are designed to handle these challenges. MIMO systems use multiple antennas to intelligently process signals arriving from different paths. Rather than treating multipath as a problem, MIMO can take advantage of these reflected signals to improve coverage, reliability, and overall network performance. Radio wave refraction. Another important propagation characteristic of radio waves is refraction. Refraction occurs when a radio wave passes from one medium into another with a different density, causing the wave to bend or change direction. This happens because the wave travels at different speeds in different materials. A familiar example is the way light bends when it moves from air into water, such as when shining a flashlight into an aquarium. In wireless communication, radio waves can be refracted by various materials including drywall, wood, glass, metal, and plastic. Since each material has different electrical properties and densities, the amount of bending varies. Although these effects are often small and indoors, they can influence signal paths and slightly impact Wi-Fi performance. Refraction is not limited to physical objects. Environmental conditions such as temperature changes, humidity, water vapor, and air pressure can also alter the path of radio waves. These atmospheric effects become particularly important in outdoor wireless deployments. For example, in point-to-point wireless links, even a slight change in the signal's path due to refraction can cause antenna misalignment, resulting in reduced signal quality, lower throughput, or intermittent connectivity. Understanding refraction helps wireless engineers anticipate signal behavior and design more reliable communication systems, especially in environments where atmospheric conditions or material obstacles can influence radio wave propagation. Radio wave diffraction. Another important propagation characteristic of radio waves is diffraction. Diffraction occurs when radio waves encounter an obstacle or a sharp edge and bend around it, creating new wavefronts that continue to propagate beyond the obstruction. This unique property allows radio signals to reach areas that are not in the direct line of sight of the transmitter. A simple way to visualize diffraction is to imagine light entering a dark room through a keyhole. Instead of remaining confined to a narrow beam, the light spreads out and illuminates part of the room. Similarly, radio waves can bend around corners, doorways, and other obstacles, enabling communication even when a direct path is blocked. In wireless networks, diffraction plays an important role in extending coverage into areas that would otherwise receive little or no signal. Combined with reflection, it helps Wi-Fi signals navigate around walls, furniture, and other indoor obstructions. However, diffraction comes with a trade-off. As radio waves bend around obstacles, they lose some of their energy, resulting in weaker signals. The amount of loss increases as the signal frequency increases. This means higher frequency signals are generally less effective at diffracting around obstacles. For example, a 2.4 GHz Wi-Fi signal typically diffracts more effectively and maintains better coverage around obstacles than a 5 or 6 GHz signal. As a result, 5 or 6 GHz networks often experience greater signal loss in obstructed environments, making diffraction an important consideration when planning wireless deployments. Understanding diffraction helps wireless engineers predict coverage patterns and optimize access point placement to achieve reliable connectivity throughout a network. Radio wave scattering. Another important propagation characteristic of radio waves is scattering. Scattering occurs when radio waves encounter rough, irregular or uneven surfaces. Instead of reflecting in a single predictable direction, the signal is dispersed into many different directions, creating multiple weaker wavefronts. A useful analogy is sunlight passing through scattered clouds. As light interacts with clouds of varying thickness and density, it is reflected and refracted in different directions, causing the sunlight to spread out. Radio waves behave in a similar manner when they encounter objects with irregular surfaces or varying structures. Unlike reflection, where a significant portion of the signal follows a defined path, scattering distributes the signal energy across many directions. As a result, the original signal becomes weaker and less focused. In wireless environments, scattering can be caused by objects such as indoor plants, textured walls, furniture, metal fixtures and other irregular surfaces. Even small objects can contribute to scattering when their size is comparable to the wavelength of the radio signal. Scattering can reduce signal strength and quality by dispersing energy that would otherwise travel directly toward the receiver. In some cases, the scattered signal may become so weak that it dissipates before reaching its destination. Understanding scattering helps wireless engineers identify potential sources of signal degradation and design networks that maintain reliable performance in complex indoor and outdoor environments. Radio wave absorption. The next important propagation characteristic of radio waves is absorption. Absorption occurs when a radio wave passes through a material and a portion of its energy is converted into heat or otherwise lost within that material. As a result, the signal emerges weaker than it was before encountering the obstacle. A simple analogy is shining a flashlight through different objects. If you place your hand in front of the flashlight, most of the light is blocked, demonstrating high absorption. On the other hand, glass allows much of the light to pass through with minimal loss, indicating low absorption. Radio waves behave in a similar way. Different materials absorb different amounts of radio frequency energy. Some materials allow signals to pass through relatively easily, while others significantly weaken the signal. In Wi-Fi environments, common building materials such as drywall, wood and glass generally absorb less energy, allowing signals to penetrate more effectively. Dense materials such as brick, concrete, stone and metal absorb or block much more energy, resulting in greater signal attenuation and reduced coverage. The amount of absorption also depends on the signal frequency. Higher frequency signals typically experience greater absorption than lower frequency signals when passing through the same material. This is one reason why higher frequency Wi-Fi bands often have reduced penetration compared to lower frequency bands. Understanding absorption is essential for wireless network design, as building materials and environmental obstacles can significantly influence signal strength, coverage and overall network performance. Radio wave polarization. The next important characteristic of radio waves is polarization. Polarization describes the orientation of a radio wave's electric field as it travels through space. In wireless communication, polarization plays a critical role in antenna alignment, signal reception and overall communication efficiency. The most common types of polarization are vertical, horizontal, and circular polarization. The polarization of a signal is determined by the design and orientation of the transmitting antenna. Why polarization matters. For maximum signal transfer, the transmitting and receiving antennas should use the same polarization. When both antennas are aligned correctly, the receiver can capture the maximum amount of signal energy. However, when there is a polarization mismatch, for example, a vertically polarized transmitting antenna communicating with a horizontally polarized receiving antenna, a significant portion of the signal energy is lost. In some cases, this mismatch can result in signal losses of up to 20 decibels or more, leading to reduced coverage and degraded performance. Polarization can also be used strategically to improve spectrum utilization. By transmitting signals on different polarizations, multiple wireless systems can operate in the same area with reduced interference, allowing them to coexist more effectively. Modern wireless technologies also take advantage of polarization. In MIMO systems, antennas often use different polarizations to create multiple independent signal paths. This enables the transmission of multiple data streams simultaneously, increasing network capacity, improving reliability and delivering higher throughput. Understanding polarization is essential for optimizing antenna placement, minimizing signal loss and maximizing the performance of modern wireless communication systems. Radio wave fading. Another important propagation characteristic of radio waves is fading. Radio wave fading refers to the variation or reduction in the strength of a received signal over time, location, or frequency. Rather than remaining constant, the signal may fluctuate, weaken, or even temporarily disappear as it travels through the environment. Fading commonly occurs because radio waves rarely reach a receiver through a single path. Instead, multiple copies of the same signal may arrive after being reflected, diffracted, or scattered by surrounding objects. When these signals combine at the receiver, They can either strengthen or weaken one another depending on their relative phase and timing. Environmental factors such as buildings, walls, vehicles, moving people, weather conditions and terrain can also contribute to fading. Even small changes in the environment can alter the signal path and cause noticeable fluctuations in signal strength. There are several types of fading. Slow fading or shadow fading, caused by large obstacles such as buildings, hills, or dense structures that block or attenuate the signal. Fast fading or multipath fading, caused by multiple signal paths combining constructively or destructively at the receiver. Frequency selective fading occurs when different frequencies within the same signal experience different levels of attenuation. In Wi-Fi networks, fading can result in reduced throughput, increased packet retransmissions, higher latency and intermittent connectivity issues. Modern wireless technologies help mitigate fading through techniques such as diversity antennas, MIMO, beamforming, adaptive modulation, and error correction mechanisms. Understanding fading is essential for designing robust wireless networks, as it directly impacts signal reliability, coverage, and overall communication performance. Let me know your thoughts in the comments if you found this video informative and helpful. In the next video, let's see free space RF propagation loss. Thank you for watching.